Pause the video, identify your variables, determine your equation, and draw a picture. The mass is given as 0.575 kilograms. It's thrown straight down from a 10.0 meter high toadstool. So if I draw a picture, I know this height is going to be 10 meters. So that is my height. If the final speed, so we know the final speed here is 18 meters per second. So my final speed is 18 meters per second. We're looking for the initial speed. So we know this is a conservation of energy. There's a height and there is velocity. So E initial is going to equal to E final. So we can have KE initial, PE initial. We can have KE final, PE final. We know we have an initial velocity because we're looking for it. We have an initial height of 10 because this is our initial point right here. We have a final velocity that is given to us, and we have no potential energy. Now I substitute in, so 1/2 mv0 squared plus mgh0 equals to 1/2 mv final squared. I'm going to cancel all the m's out because they're the same. And then afterwards, I'm going to multiply the entire thing by 2 to get rid of the half from velocity initial. So that becomes v0 squared plus 2gh0 equals to v final squared. I'm going to subtract a 2gh0, subtract a 2gh0. This cancels out. So v0 equals to v final square minus 2gh0, take the square root. So v final squared becomes 18 meters per second squared minus 2 times 9.8 meters per second squared times 10 meters. And then you have to take the square root. You should get 11.31 meters per second. So if you notice, if there's a height difference with velocity, it's usually a conservation of energy. Since no spring is present, we know that we're going to have potential kinetic at the end, and we cross out anything that's not possible. So if there is no height, we cross out the potential energy. If there's no velocity, then we cancel out the kinetic energy. So pause the video, identify all your variables, and determine what equation you should use. This is also a conservation of energy. How do you know? We have a block that's 5 kilograms, and they want to know how much potential energy is at the top and what speed it slides down. So this is pretty straightforward. So potential energy is equal to mgh. And we know the mass is 5.0 kilogram. Gravity is 9.8 meters per second squared. And my height is 6.5 meters. Remember, this is still work. So potential energy and the displacement must be parallel. So this becomes 318.5 joules. Next it asks, what is the block's velocity at the bottom? So this one we know is a conservation of energy. Remember, we cannot use kinematics on the test. So again, the only energy possible is kinetic energy and potential energy because there is no spring. Kinetic energy at the beginning is 0. We have all potential energy because we are starting at the top. Kinetic energy final we will have because we're looking for a speed at the bottom, and at the bottom there is no potential energy because there's no more height. So this becomes mgh naught equals to 1/2 mv final square. The masses cancel out. So I'm looking for V final, so I need to multiply everything by 2. So this becomes 2gh naught is equal to V final square. Take the square root. So V final is equal to square root of 2gh naught, or 2 times 9.8 meters per second squared times 6.5 meters. And then take the square root. And you should get approximately 11.29 meters per second. So here we have a block that's being pushed up a ramp. So first thing you want to do is identify your variables, draw any free body diagram when necessary, and write your equations from the variables that you identify. So we know we have a mass of 5 kilograms. We know we have an applied force needed to push, and that is my 52. So that means I know my applied force is going up the ramp. I need to find the work done by the block, work done by gravity, and work done by friction. So whenever I do work problems, the first thing I need to do is read the problem carefully. You only do the work that it is asked for. Since they want the work done by the block here, the work that is done on the block is by the applied force. So that means the force that I use is my applied force, 52 newtons. My displacement is 16 meters. I do not have to do sine or cosine, because if you look at my applied force, this is parallel to my displacement. So all I need to do is multiply these two numbers. So if I do that, I should get approximately 832 joules. Next, they want the work done by gravity. The work done by gravity is the weight, or the gravitational force. If I draw my weight, it is going to be perpendicular to the earth, Fg. So the work here is going to be Fg, because that's the force we're talking about, times the displacement. If I use Fg itself, I need to find the displacement that is parallel to that. The displacement currently given is the ramp. So that means I need to find the height of the ramp. So this is my 16 meters that was given to you. My angle is my theta. Since h is opposite the theta, the formula we're going to use is sine theta, which is opposite over hypotenuse. So I'm going to multiply both sides by hypotenuse. The hypotenuse on the right side cancels out. So opposite is hypotenuse sine theta. And if you notice, that is your displacement here. So my h is going to be d sine theta. And now if you notice, these are parallel. So Fg is now mass times gravity, because that's my weight. Height is d sine theta here. This right here is height, because we are talking about the vertical distance. I could also do this problem over again, resolving the weight component. If I resolve the weight component, I need to draw my normal in perpendicular to the earth. I resolve that into fx and fy. So that means fgx is opposite my theta. So that becomes fg sine theta. And fg we know is mg, so sine theta. Fy is next to, so it's going to be Fg cosine theta. So this is mg cosine theta. So if you notice, the component that's parallel to the 16 is fgx. So if I resolve this, this is fgxd, which is also mg sine theta d. If you notice, the formula is exactly the same. So I could plug in for either one, the top one or the bottom one. So this is going to be 5 kilograms times 9.8 meters per second squared sine 57 times 16 meters. You should get 658 joules. Next one, I am going to do the work done by friction. The work done by friction has to be the frictional force times the displacement. So if I draw my frictional force in the diagram, it's going to go down the ramp, opposing the motion. And we know friction is equal to mu n. And we know we need to solve for n. To do that, I need to write a sum of Fy. N is going up, so I'm going to make it positive. It's going to be opposed by Fgy. This is equal to Ma. Ma is equal to 0 because there is no acceleration in the y direction. So N is Fgy or mg cosine theta. So if I plug this in, this becomes mu n d, which is equal to mu mg cosine theta. So that's friction right here, times d. I do not have to resolve the d, because if you look at my force friction vector, it's going down the ramp, and the displacement given is along the ramp. So these two are parallel. So now all I do is I plug in. My mu is given as 0.39. Mass is 5.0 kilograms. My gravity is 9.8 meters per second squared. Cosine 57 times 16 meters, which is 167 joules. The other way I could done this a little bit easier is, I know my work net has to equal to 0. Why? It's traveling at a constant velocity. If it's traveling at a constant velocity, we know that work is equal to force net times displacement. So that means at constant velocity, my F net has to be 0. So 0 times d is 0. And what is my work net? I have what? I have work from the applied force. I have work from the gravitational force, or the force due to weight. And I have work due to friction. This is equal to 0. So if I need to find friction, I already know work due to weight is going to be 832 joules, and it is positive. Why? My force applied is going up. My displacement is in the same direction. My force gravity is going to be negative. The reason it is negative is my force is going down the ramp. My x component, if you look here, is down the ramp, but my displacement is up the ramp. So since they're going in opposite direction, this is negative. So that's going to be negative 658 joules plus WF. This has to equal to 0. So if you notice, WF is approximately 174 joules, which is close enough here because we rounded a lot of the values as we went along. So that's another way to do it. Power is the rate at which work is done. Power can be written as equal to work over time, in which work could be F times D. We know work can also be kinetic energy, so it could be 1/2 mv squared. We also know work can be potential energy, so it could be mgh. So it could be substituted in for any of these. Over time, it could also be written as force times velocity. Why is that? We know that work is equals to force times distance, and we know that it is divided by a time, and distance over time is the velocity. So these are the two formulas for power. The units for work is joules. The unit for time is seconds. These are SI units. And so a joule over a second is watts, or a capital W. 12 kilogram block is pushed up on a 8-meter ramp at a constant speed of 2.5 meters per second with a force of 28 newtons. So the length of the ramp is 8.0 meters. We know the speed is 2.5 meters per second. And we know the force is equal to 28.0 newtons. Calculate the power. There's multiple ways to do this, but the easy formula is power is force times velocity. The force is 28 newtons times my velocity, which is 2.5 meters per second, which is equal to 70 watts.